Hello, everybody. My name is Josiah Hagen. I'm a security researcher at Trend Micro, using artificial intelligence and machine learning techniques in order to find what the bad guys are doing and stop them from doing it. Today, I'm going to talk to you about a survey of similarity for security. This is math class, so if you find yourself in the wrong room, better head for the exits now. Let's dive in. So why would we want to look at similarity as a tool? Well, we need to understand what tools, what techniques, algorithms group what samples, whether they're files like PE or ELF, whether they're shell code, HTML, spam. We need to know how to group these things together, because the bad guys, they're always trying to hide what they're doing. And if they don't change what they do enough, we can find them by finding patterns similar to ones that they have used before. Also, everybody's making a ton of data. This means that even in the DevOps world, we're rolling out new compilations of programs every hour. And so we have new cryptographic hashes for programs that are effectively not different, but were just compiled at different times. So we need to be able to sort through all this information and find the things that group together. Now, how can we tell if a similarity measure is useful? Well, we need to know how well it performs in search and clustering. In particular, we want to know if we have something, whether it's similar to something we've seen before, in which case we're doing search, or when we have a vast sea of data, whether we can group these things together in order to triage them en masse, so that when we deal with several things from a cluster, we generally understand what's going on with a whole group of information. We also need to consider scaling, especially the runtime complexity. Disk is cheap, but time is money, so we care about runtime. Finally, we're in an adversarial setting, so we need to look at the anti-evasiveness of the techniques that are being used and make sure that they're not too easily defeated by cheap changes, by easy changes. So at the end of this talk, I hope that y'all will understand the following algorithms. In the beginning, we'll do some preliminaries, like look at several versions of edit distance. We'll look at the Jaccard Similarity. And we'll also look at the data structure Bloom filters, because all three of these things underpin a number of similarity techniques. Then we'll move on to the body of knowledge for similarity for security, including SSDeep and later SDHash, and then LZJ. And finally, we'll finish with work that we've done at Trend in locality-sensitive hashing, including TLSH and more recently, Elfhash. At the end of the talk, you should know about all of these things. So let's warm up. When people talk about edit distance, they might mean a few things. Most basically, we should consider the Hamming distance, which is used to compare two bit streams to each other. And they do this simply by counting the places where the values are different. Very simple. You just count them up, you have your Hamming distance. Then there's the Levenstein distance, which is what people normally refer to when they talk about the edit distance. This counts the number of insertions, substitutions, and deletions to get from one string to another. You can use dynamic programming to solve this in linear time, which is good. Comparing A to B in linear time is certainly handy, but there's no way to save this information. Every new thing you get, you have to compare to everything you've seen before, and so search is linear in time with respect to the size of the corpus, which is no good. Clustering is even worse. So how does edit distance work? Well, if we want to turn intention into execution, we might do a deletion, a substitution, another substitution, an insertion, and then finish with a final substitution, which gives us 5 operations. And so the edit distance from intention to execution is 5. Next, we need to understand the Jaccard similarity. This is simply what appears in both sets over what appears in either set. And you just measure the size of these two values, the cardinalities. And you're really looking at the intersection of A and B over their union. Now, this requires some feature engineering, right? We're not just talking about editing from one value to another. We're talking about sort of features, because if we were just looking at bytes and we did this, we would quickly run into the fact that maybe all of the byte values appear in both sets, and 1 over 1 is 1, which is not interesting. Everything would be similar to everything else. So you need to pull out larger things as features, which may be n-grams or substrings that appear in either or both of the sets. You could look at imports if you're dealing with file, PE, for example. You could put imports into a big set and see what they have in common over, what's in both. Like edit distance, you can only use the Jaccard similarity pairwise, which is a big limitation. However, if you do save the features, then what you're doing is linear with respect to the feature corpus, which is better than linear with respect to the whole corpus, since your features are likely to be a smaller space of information, you'll have smaller runtime complexity, but still, you still have to go through everything again in order to determine if you have something similar to what you had before. So visually, the Jaccard similarity, the intersection over the union, is where the sets overlap versus the totality of what is in both sets. If you want to look at how this is used in other algorithms, we can look at minhash, but we'll come back to that later. Finally, in this warm-up section, we have the Bloom filter data structure. Now, this is not a similarity measure, but is a space-efficient lookup table, and it's a handy tool to have in your pocket. So it uses a set of hashes for compression to determine whether some feature is not in your set, not whether it is in the set, which it sort of determines probabilistically, but it can reliably determine whether your thing has not been seen before. This is useful to have. So how does it work? Well, let's say we were looking at gene data. We might take the sequence ACC GTAD and look at the 4 grams in it, which is the subsequences of length 4. And for each of those, we'll hash it to a bucket and we'll put a 1 there if we've seen it. And so when we come along with a query string, the CGTAT, we can say, all right, let's look at the subsequences of 4, the 4 grams in there. And the first one we look at, and there is a 1 in the bucket. So did we see it before? Don't know, but we know that we did not see it. And so we move on to the next one and we see GTAT. We hash that, we get to a bucket with 0, which means we know we have not seen this before. This subsequence does not exist. And so our query string does not exist within the data. Okay. None of these techniques previously described scale as desired. So we need to do something else. Kornblum came along and developed SSDeep a while back. And the idea was to make the feature corpus small and predictable. He used a context-triggered piecewise hash, which is to say that you chop the stream up into segments, and then you keep a rolling hash, which is an algorithm that he got from SpamSum, which is where the SSDeep SS comes from. And for each of these chunks, you're going to emit a 6-bit value at the boundary of that chunk, and then keep going and emit more of these. Okay, so that's how this is a piecewise hash, because different pieces are emitting different values. This is recorded with the block size, and in the end you end up with a 64-byte fuzzy hash, which is to say, if things started off close together, let's say with the edit distance, then their resulting SSDeep digests would be close together, even just visually. What does this give us? Well, it gives us search that's in linear time with respect to the number of elements, because the 64-byte is not going to drag everything around. There may be a 64x constant in front of everything, but that's nothing compared with scaling in terms of the number of elements. This is runtime efficient. That's great. How does it work? So here's how we build the context-triggered piecewise hash. We're going to go through every byte in the input, and we need to know where to chop it up. So this rolling hash is used to check for boundary conditions. And then every byte, we're also going to update these 2 traditional hashes, which will only emit after each block, and then in the second case, after every other block. So again, when we're checking for boundaries, we're going to look at whether we're on a block boundary or whether we're on an every other block boundary, these 2 cases. And then we're going to update our signature by taking our traditional hash and projecting it down to a 0 to 63 value. So we're going to mod 64 it and just emit 6 bits of a compressed value of this already hashed thing as part of our signature, concatenate and move on. So how do we compare two digests? We end up with these digests that have this block size, colon, one signature, colon, the even block signature. When we compare them, we need two digests that are two fuzzy hashes that have equal block size, or one of them must be 2 times the size of the other, so that we could compare, for instance, signature 1 from A versus signature 2 from B. Now, in calculating the comparison, SSDeep uses a weighted edit distance of these digests. So it measures the changes with insertions and deletions getting a weight of 1, substitutions getting a weight of 3, and reversing operations getting a weight of 5. Final score is scaled with 0 indicating no match at all, and any other positive number, any other number indicating that there is some matching substring in these sequences, and so they are some way homologous. It is fast and accurate for substring matching on same-sized inputs, so this is good news. But many data are incomparable. We cannot compare things that do not have the same or 2x block size, which means a lot of things we just don't know whether they're similar or not. Furthermore, we know it's easily defeated by reordering. It'll totally mess up the rolling hash. Padding can do the same, reformatting can do the same. And so SSDeep is easy to evade, which does not meet our criteria. So Vasily Rusev came along and developed SDHash in order to improve upon forensic tools available for similarity. And his idea was to find the interesting parts of the file, which is an interesting idea, I think. In particular, SDHash uses 64-byte sequences as features. So there's a window that slides so that bytes 0 to 63 are a feature, bytes 1 to 64 are a feature, and so on. The entropy of each of these 64-byte subsequences is a hint as to whether this is interesting or not. So tables, for instance, in JPEGs or whatever, are very high entropy. They cover a lot of the space of possible byte values, but they're not very interesting. And so what you do in SDHash is for different file types, you order the likelihood of entropy values, and you get a precedence rank of entropies, with the ones that are least likely being more interesting. This allows you to construct a similarity digest from unlikely features, and that's where the SD in SDHash comes from. Now, it sort of begs the question, what's precedence rank for a given file type? And it means you need to profile the features for different file types in order to really do this as described. Otherwise, you'll have a profile that matches some sort of general data that may not have the entropy distribution appropriate to the data that you're looking at. So how does it work? Well, again, we're going to look at the interesting 64-byte sequences based on the precedence rank. Now, place each of these features. So you're going to take some 64-byte sequence and hash it, and with a number of different hashes, as usual, into a Bloom filter. And then if your Bloom filter fills up as you're going along and doing this, you're just going to tack another one on. And you're going to keep doing this operation, and you're going to emit as an SDHash a sequence of Bloom filters. So how do you compare two sequences of Bloom filters? You use a Hamming distance across Bloom filters. Really well understood how you can compare Bloom filters. And so all you have to do is look at the bits where they are different, because essentially they're like a dictionary with flag values, right? Does this thing not exist in here? And you can just measure, do these agree or disagree for two of these Bloom filters. In particular, since we have a sequence of them, what we do, assume that n has a smaller sequence of Bloom filters or less than or equal to y. We'll go through all of x's n Bloom filters, and we'll look for the max distance among the m Bloom filters in y between x and y. And we sum that up and divide by the number in n, and that gives us our SDHash distance. Well, it is better at similarity than SSDeep. It's definitely shown in a number of experiments in literature that its ability to perform search it's much more robust than SSDeep. However, digests that it creates are still 2 to 3% of the size of the original stream or original file, which is not much smaller. We don't know exactly what the magic profiles are for particular file types. We know that they should be different from file to file, but in practice, it's not used in a way that is very sensitive to a myriad different file types. And, will these profiles change over time? For instance, HTML in 2020 looks a bit different than it did in 2010. The distance in comparing two things is not a metric or an approximate metric, which can lead to more problems down the road in terms of what other techniques from the machine learning toolkit are available to. So search is roughly linear with respect to the corpus size. You do save that, you do get from 100% of your corpus down to 2%, but it's still a lot of data that you're looking at in order to compare one thing to another. And clustering is even worse. So this requires a new approach, and Edmund Raff came along and decided that this notion of Kolmogorov complexity, or what is the shortest way that we can encode a given string, was useful in terms of understanding how we can compare two things for similarity. Now, Kolmogorov complexity, like what is the shortest way I can encode X, is impossible to compute because of something that Gödel said about us not being able to understand the system from within the system. And so we can only approximate it with compression. And people have been using this a bit as an approximation for the complexity, because compression is how we go about making things as small of an encoding as we would hope to get. This LZJ uses an edit distance like concept where you take one stream and say, how can I encode the other with it? And it also uses this notion of the compressed size as, the cardinality of a set might instead be replaced with the compressed size of the stream. From this, we can get the normalized compression distance that we could encode one stream with another. So if we look at it, the numerator there, we're going to look at the compressed size of concatenating X and Y. Imagine if they were not exactly the same file, but they contained largely the same long runs of sequences. It might be that compressing their concatenation really adds no more length. And so when we subtract the minimum length from the compressed size of one or the other, that number may get very close to 0. And then, of course, we scale based on what the maximal size of the compressed value is for one stream or the other. So this is pretty cool. It has a good idea behind it, and we'll look at how it is they construct these LZ sets. Really, you want a way of getting the subsequences that occur in a runtime efficient manner. So what you do is, you start with an empty set for your LZ set in the beginning. You go through your stream with a starting and ending pointer. And at first you just consider, the first byte. And if it's not in your set, then you add it to your set and you move your starting pointer forward. Now, in any event, you'll move your ending pointer forward, which is how you get to the end. And this allows you to sort of move along in the byte stream or in the sequence and get variable length subsequences if you have not seen the things that that are in there. Then you start over. But if you have seen, for instance, AB before, then you keep going and see what comes after AB and you add that. So if it's ABZ, then you'll add ABZ to your LZ set. So recall the Jaccard similarity was the intersection over the union. The Jaccard distance would be just 1 minus that value. And so they authors define the LZJ Jaccard distance as 1 minus the Jaccard similarity of the LZ set of one with the LZ set of the other. So you calculate these sequences, you store them, and you see what's shared, what their intersection is, over what their union is. This is great. You know, the way that they're constructing the LZ sets is it's going to be, you're going to be able to construct these LZ sets linear with respect to the corpus length. But it can't scale with all these subsequences because you have variable length. You know, if your subsequences get long, you may not actually compress as much as you would hope. So instead, the authors also proposed this hashing version, this LZJ, LZJH, which hashes the subsequence and gives you a 4K fixed digest, which I'd like to see. It uses a Bloom filter that has a set of hashes, and then the fact that the min hash trick with the k smallest hashes allows you to get to the Jaccard similarity. So the probability that the minimal hash over A is equal to the minimal hash over B is the same as the Jaccard similarity. We won't prove that today, but this allows you to approximate the Jaccard similarity by looking at the union across k minimal hashes from A and the union across k minimal hashes from B, and use these as your LZ sets. It's very runtime efficient, but we're still working on a 4K digest, and it's not exactly a linear comparison operator either. So there are some things that make me say that none of the techniques previously described scales as desired. So at Trend, we decided that we need something that can generate a digest in linear time. None of the things that we would consider are going to be less or more than linear time. We have to look at everything exactly once, and we want to make sure we don't have to look at it any more than that when we're doing static analysis. So TLSH, Trend's locality sensitive hash, looks at doing this with byte sampling on the input. Really, it does this in a way to create a histogram of n-grams in a 32 byte space. So the output's this histogram, which is encoded in 32 bytes, that represents not whether something has been seen, but how often it's been seen, at least relative to the other things that we've seen. In order to deal with, you know, the bad guys trying to work around it, we use k-skipped n-grams as a way of sampling. Instead of just normal straight runs of subsequences, we might skip a few bytes here and there in collecting our subsequences, because this sort of oversampling makes singular changes have less effect on the output, and also means that, you know, even more changes are not going to ramp up the differences substantially. That we sort of have this oversampling regularization, which makes it harder to make small changes on the inputs have large changes on the outputs. We also deal with some edge cases, namely if we're looking at histograms, we want to also consider that they're proportional and that the files might have different lengths. If we took the same sequence and repeated it, you know, 1,000 times, the histogram would be the same, but the length clearly would be much different. Also, this is a compressive activity. We are projecting a lot, and so we may have collisions. So we may have the same histogram, but not the same byte stream. And so just add a way of determining if actually it's likely that your two inputs exactly match. And then finally, we have a distance that is an approximate metric, which will allow us to use other tools from the ML toolkit in order to do things very efficiently. So let's first talk about what these k-skip n-grams are. Here in the standard implementation of TLSH, we use k equals 2 for a 2-skip 5-gram, What that means is that we're sliding a window over 5 bytes and gathering 3 grams, sequences of 3, not necessarily contiguous, and hashing those sequences to buckets. So what does that look like? Well, in a sliding window over 5 bytes, skipping 2, we have these 6 different sets of 3 bytes that we'll gather and hash to buckets. And then as we slide the window along, we'll gather 6 more sets of 3, and then 6 more sets of 3 until we get to the end of the file. This sort of convolution means that small reordering or permutations are not going to have a large or much effect at all on the end result of the histogram. So how do we create the digest as we're hashing to these buckets? Well, we select these 5 bytes and we've got 6 different 3-byte subsequences that we're then going to hash into the buckets at the bottom, where we're just going to increment counters based on how many times we've hit that bucket. So now we've got a bunch of buckets and we need to emit a digest. Well, what we do is we split the buckets up by what quartile of buckets they're in. If they're in the first quartile, then a quarter of the buckets are below that number value of number of times things got into the bucket. If they're in the fourth quartile, then only they're the highest value where only a quarter of them hash to that bucket. So we go along, and for instance, in this sequence, we have our bucket n is in the second quartile. So we emit 2 bits, which here corresponds is the 0, 1 for we're in the second quartile. And then if we're in the final quartile, we emit a 1, 1. So and we have 0, 1, 1, 1. And then we're in the third quartile, we emit a 1, 0. If we're in the second quartile, 0, 1, 1, 0, 1, 1. And so we take these 2 bits for what quartile we're in for each of these 128 buckets and concatenate them together in order to have a representation of the histogram of where we hash things to buckets. How do we compare 2 histograms? Well, we take the one on the top and compare it to the one on the bottom. We see for the first 2 buckets, the lines appeared in the same quartiles, right? And then in the third bucket, we see they're vastly different. We see the top one is in the fourth quartile, so we get a 1, 1. It's in the first quartile on the bottom distribution, so we get a 0, 0. We see they're also different on the next one, where the top one is in the bottom quartile for 0, 0, and the bottom histogram is in the second quartile for 0, 1, and so on. So what we do is we compare each of these 2-bit values, and we construct the distance as follows. If the 2 bits are the same, we will not add anything to the distance. If they're 1 apart, we'll add 1. If they're 2 apart, we'll add 2. If they're 3 apart, for instance, if one is in the first quartile and one is in the fourth quartile, then we'll add 6. Really, that's the only case that there'll be 3 apart. And the reason we add so much is this corresponds to the probability that this sort of thing could happen. So we also need to account for the length. As I mentioned, if the length bytes differ, so we store the length as the logarithm, base 2 of the length. So if the bytes differ, then we know that they're off by at least a factor of 2. And so we increment the distance by 12 times the factors of 2 that their lengths are different. And then finally, we account for the checksum, which is we either add 0 or 1 to the final distance, depending on whether the checksum byte is the same, which you could just have like a rolling CRC that its chances of being the same for 2 different files is roughly 1 in 256. So it gives us at least a probabilistic way of saying that these were indeed or not the same thing. So how well does this work? Well, we can calculate digests in linear time with respect to the corpus, which we can't really do better than because we have to look at everything at least once. Now, importantly, because it's an approximate metric, we can do search in logarithmic time with respect to the corpus. And we can cluster in n log n time with respect to the samples. So these are the scaling numbers that we really want to look at and that we really want to see for any tool that we're going to use, because If we have to search in linear time, we're going to spend a lot of time as we add sample, just going back and looking to see if we know that this thing is in there. If we can get to logarithmic time, then we have something that we can actually use at a large scale. Same with clustering. We want to avoid the curse of n squared, and we want to get the runtime down. And by putting things into a search tree using an approximate metric with k-nearest neighbors, we're able to do this in roughly n log n time. That's great, but how well does it cluster things? Well, don't take our word for it. Symantec put this up on their site where they said that TLSH performs way better than SSDeep, for instance, and it's very reliable at recognizing variants of the same software when the code changes. It's preferable when dealing with source code changes, and a lot of the changes that malicious actors make are along these lines. Note that the stuff that's not highlighted also says that SDHash performs well when recognizing the same program compiled in different ways. And when you have a gap, what do you do? You fill the gap. See need? Fill a need. So we had to develop Elfhash to deal with particularly the messy world of ELF files. If we want to talk about compilation differences, ELF, you can have the same thing compiled across different architectures, and symbols are far more generic than PE. You're more likely to have dynamically linked versus statically linked binaries, with stripped symbols being more likely. So it's a lot harder to determine that two things which are actually the same are the same, because a lot of these tricks are often taken to hide things. So as an aside, let's consider ImpHash, which was developed to look at PE imports. It concatenated all the imports together and then took a straight cryptographic hash to make a fingerprint of the imports. Now this is better than you might expect in terms of identifying similar PE files, but it's still not good enough. Clearly, you just need some call substitution, library substitution in order to end up with something that's completely different than other things. But the idea behind it is helpful, and Elfhash borrows that idea. So how does it work? Well, if you don't have symbols, then what you need to do is extract the function called destination addresses and put all of those into your signature. If you do have symbols, but you're not statically linked, then you need to extract the external symbols, and you put those in your signature. If you are statically linked, then you can extract the internal symbols and then put those in your signature. And for all of these, there's going to be some filtering where you move symbols that are not related to external calls, and you remove some specific symbols. Sort it, and then do TLSH, and you have something that works on ELF files. So the final test for all of these is standardization. Cyber threat intelligence and indicators of compromise should include fuzzy hashes, because you might not actually have the same samples, but you might have similar ones. STIX 2.1 as an interchange format includes TLSH and SSDeep, interestingly, probably because both are compact and have standardized parameters. It makes it easy for people to share these things. We know which one we believe is much better. We're also seeing more widespread adoption now for TLSH, not just academically, but also with free tools that enable people to use TLSH and Elfhash. SSDeep has been there for a while with search, but now people can use TLSH for search and clustering, and TLS can use Elfhash for dealing with ELF and especially IoT. So that's all we have time for today. I hope you would agree that math is fun, maybe hard, but it pays to learn, because this is all the stuff you need in order to find things which are similar. Thank you very much.